In the vast, silent darkness of the cosmos, two particles drift apart. One travels left, one travels right. They move so far from each other that even light, the fastest messenger in the universe, would take years to bridge the distance. And yet, in a way science still struggles to explain, these two particles are not separate. They are connected, bound together by an invisible thread woven through the fabric of reality. A change in one instantly appears in the other. No delay, no distance, no signal traveling between them. Einstein looked at this and whispered, "Spooky action at a distance." This is the story of quantum entanglement, the most mysterious, most unsettling, and most awe-inspiring phenomenon in all of physics. A story of hidden connections, broken rules, and a universe far stranger than we ever imagined. Imagine two coins, spin them, let them settle under two distant cups, one here on Earth, one on a distant moon. Now imagine lifting one cup, and the instant you see the result, heads, the other coin, light years away, also locks into tails. Not after a delay, not after waiting for information to travel. Instantly, impossible, ridiculous. And yet, this is exactly what entangled particles do. They share a state, not a physical connection, not a hidden message, a shared reality, a single wave function stretched across space. Two bodies, one story. The journey begins in the early 20th century, the dawn of quantum mechanics. Scientists uncover a truth they're not ready to face. Particles behave like waves. Waves overlap. And when waves overlap, they can become one. This merging of wave functions creates entanglement. Picture two ripples forming on a still pond. They expand, collide, and merge into a single, unified vibration. From that moment forward, their fates become intertwined. In quantum physics, this merging happens not in water, but in the invisible space of probability. Two particles become described by one shared equation. Their properties do not exist independently. They exist only in relation to each other. Measure one, you know the other. Change one, the other responds. Distance does not matter. Separation is an illusion. Albert Einstein, the man who reshaped space and time, found himself terrified by this idea. To him, entanglement was not a discovery. It was a warning sign that quantum mechanics was incomplete. He believed physics must obey one sacred rule: nothing can travel faster than light. Yet entanglement laughed at this rule, mocked it, shattered it. Einstein, Podolsky, and Rosen published the famous EPR paradox, arguing that entanglement proved quantum mechanics was missing some hidden variables, unseen instructions inside particles that predetermine the outcomes. They thought they exposed a flaw, but instead they exposed the universe's greatest secret. For years, physicists debated, is quantum mechanics incomplete? Are hidden variables secretly determining everything? Or is reality itself fundamentally non-local, connected beneath the surface? Then came a quiet, brilliant Irish physicist named John Bell. In 1964, Bell derived a set of inequalities, mathematical conditions that any hidden variable theory must satisfy. And when experiments tested Bell's inequalities, the results were shocking. Quantum mechanics was right, Einstein was wrong. The universe is non-local. Entangled particles do not carry hidden instructions. They do not choose outcomes in advance. Their properties do not exist until the moment of measurement. And when one is measured, its entangled partner snaps into a matching state instantly. Reality, it seems, is stitched together by invisible threads. Physicists have tested entanglement across continents, between islands, across mountains, even between Earth and satellites orbiting in space. Every time, the result is the same. The connection is instantaneous, not fast, not incredibly fast. Instant. If there is a signal, it travels at least 10,000 times the speed of light, and probably infinitely faster. This is not communication, not information transfer, not cheating the speed of light. It is something deeper, a single quantum system spread across space, two ends of the same cosmic string. To understand entanglement, visualize the universe as a vast ocean. Particles are not tiny marbles floating in this ocean. They are waves rising within it. When two waves meet and merge, they remain part of a unified pattern, Even if the ocean later carries them far apart, they share a memory, a connection, a synchronized rhythm. Entanglement suggests that space is not truly empty, not truly separate, not truly distant. Beneath the fabric of reality, everything may be connected by an invisible quantum field, a silent structure linking all things, an underlying oneness, not mystical, not spiritual, physical, mathematical, measurable, real. Quantum entanglement forces us to abandon familiar ideas. A particle does not have a definite state until measured. Its entangled partner shares this uncertainty. The pair behaves as a single object even when separated. This destroys the concept of classical realism, the idea that things have definite properties independent of observation. The universe, it turns out, does not commit to reality until it must. Measurement does not reveal the world, it creates it. And entanglement proves that creation can happen simultaneously across vast distances. A decision made here shapes reality over there. Today, entanglement is no longer a philosophical debate. It is an engineering tool. Quantum teleportation uses entanglement to transmit quantum states from one place to another. Not matter itself, but information about matter. Quantum encryption exploits entanglement to create unbreakable codes. If an eavesdropper tries to read the message, the entanglement collapses, revealing the intrusion instantly. Quantum computers rely on entangled qubits to explore many possibilities simultaneously, performing calculations classical machines could never dream of. We stand at the threshold of a new era, a world powered by entanglement, a world where technology harnesses the very fabric of reality. If two particles can be entangled, can two humans? Not biologically, not psychologically, but physically? Experiments have entangled diamonds, superconducting circuits, large molecules thousands of times bigger than atoms. The boundary keeps expanding. The question is no longer, can macroscopic objects be entangled? The question is, where does entanglement stop? Does it stop at all? Could stars be entangled? Could galaxies? Could the entire universe be one giant entangled wave function born from the Big Bang? Some physicists believe yes. Some believe everything we see is the shattered remnant of primordial entanglement, connections forged in the first moments of creation, a universe that began as one and never truly separated. Pause, take a breath, look at your hands. Every particle in your body and every electron, every proton, every atom was once fused in the heart of ancient stars. Before that, they were born from the same cosmic explosion, the same moment of creation. There is a possibility, a haunting, beautiful possibility, that through quantum entanglement, every part of you is still connected to every part of the universe. You are not separate from the cosmos. You are an extension of it, a continuation of it, a ripple in its infinite ocean. Entanglement is not just a theory, it is a reminder that reality is not built from isolated pieces, but from relationships, not from particles, but from connections. In the end, entanglement is more than a phenomenon. It is a message etched into the code of the universe, a message that whispers, distance is an illusion, separation is a story we tell ourselves. Reality is woven together more tightly than we can imagine. Two particles, once entangled, remain connected forever, no matter how far they drift, no matter how dark the space between them, a bond unbroken, a link unshaken, a thread of meaning stretching across the void. This is the hidden architecture of existence. This is the strange heartbeat of the quantum world. This is quantum entanglement.